So, we will first define the statistical specification of a random sequence, and with this hopefully we should be able to define what stationarity is of a process. We will learn what stationarity is and what the strict sense stationarity, and there is another concept called the wide sense stationarity, and we need to know the definitions for both of these results. And I think with this sort of you should be set for the rest of the course. Statistical specification of a random sequence. A random sequence x of n is said to be statistically specified by knowing the nth order probability distribution functions for all integer times n greater than or equal to 1, for all integers n greater than or equal to 1, and times which is small n plus 1 so on till small n plus capital N minus 1. So, a random sequence x of n is said to be statistically specified by knowing the nth order probability distribution functions for all integers capital N greater than or equal to 1 and times small n, n plus 1 so on till n plus n minus 1. So, that means fx xn plus 1 so on till x n plus capital N minus 1 and times n plus 1 dot n plus capital N minus 1. This is basically the probability that this variable, random variable, is less than or equal to x of xn, x of n plus 1 is less than or equal to x small x n plus 1 dot x n plus n minus 1 is less than or equal to x n plus n minus 1. Now, how do you define the probability, right? You basically probability that this continuous random variable, if I have to compute the probability, basically I integrate from minus infinity to some point a, right, of the density function, right. So, if I say probability for a discrete, I can say probability that x can take this particular value, I can exactly specify, right. For example, if it is a Bernoulli random variable, right, with zeros and ones and with probability p and 1 minus p, I can say what is the probability that this x is a 0 or x equals 1. But for continuous random variables, I cannot say exactly what is the probability of a particular that this random variable takes this particular value, because it is going to be 0, right. So, basically you can say the probability that this event x is less than or equal to some number right, some number specified, what is the probability this is that, then you can basically integrate. You can look at the integral of this density function from minus infinity to that point, right. This is exactly what we have here. I give you some values x small x suffix small n, x suffix n plus 1, that is at different times I give you these values specified at times n, n plus 1, so on. Now we have the random variable x of n, right. I told you that if you have a random process, if you basically fix a time value, it becomes a random variable, right. Now if I want a distribution of this, if I give you a random sequence x of n and I say that this is statistically specified, that means I am interested in the probability that x of this random variable x of n is less than or equal to some small x n, right, because it is random variable at this time step small n, right. I can basically specify that what is the probability jointly that at this time this random variable is this is less than or equal to this, at this time n plus 1 this random variable is less than or equal to x of n plus 1 dot 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 till the times that are specified. Okay. So this picture should be very clear in your mind, that we have a process, we are sampling this process at different times, and at different times we have these random variables, and over these random variables we want to define the probability distribution function, as opposed just to a probability distribution function or a probability density function that you can define for a univariate case or a multivariate case. Okay. That sampling is very important, sampling this random process at different times, specification of this in terms of this distribution. Now so the representation we had by specifying the probability distribution function is an infinite set of probability distribution functions for each n, each capital N, because for all times minus infinity less than n less than infinity, we need to know the joint probability distribution function. Probability distribution function is also called CDF, cumulative distribution function, right. You have to distinguish probability density versus probability distribution function. So we can, so once you know this distribution function, I think this is very important, because you, for every value of capital N, for every value of capital N you have to know all this distribution for all these times, right. So I give you some integer capital N, n equals 1, n equals 2, n equals 3, for each of those integers I need to compute the joint distribution for all these times, right. So unlike one probability distribution function that you see, the concept in random processes is you find that this statistical specification has basically an infinite set of probability distribution functions for each n, for each integer n. Now I think this is sort of consistent. We can define the mean, which is the expectation of x of n, which is basically, for the continuous case, is this is this just taking the statistical expectation, this is for the continuous case, and for the discrete case is basically you have a probability mass function and you can compute okay, that is random variable at this time takes this value, average over all possible values it takes. Clear? So that means you can imagine that this mean is a function of the index, potentially could be a function of this index. So basically we also have some extensions or classifications of random processes. So let x and y be random processes. They are a uncorrelated if r x y of t1 t2 is mu x of t1 times mu y of t2 conjugated, where r x y of t1 t2 is defined by our familiar cross correlation specified at times t1 and t2. You can define orthogonality for random processes. So if r x y of t1 t2 is 0 for every t1 and t2, for all t1 and t2, then these two processes are orthogonal, right. Imagine this is like the inner product, but we are taking expectation on a product, right. Under that measure this is 0. So therefore the natural dot product, I mean thinking about vectors or signals that are deterministic, taking the inner product whether it is in whichever space that we want to look at the inner product, and or the in the integral norm or in whichever sense we took the inner product, right. We could take the inner product, and if that happened to be 0 we said it is orthogonal. Similar to that sense we can define orthogonality for random processes, that r x y of t1 t2 is equal to 0 for all times t1 and t2, then these two processes are orthogonal. It is a very important idea. Just imagine for every such 2 times you take these products, right, x of t1 and y conjugate t2, and then take the expectation, average it out, and it has to be 0. It is a very very powerful concept. Then there is something which is more basic, which is independence. If for positive integers n, the nth order probability distribution function of x and y factors, that is f x y of x1 y1 x2 y2 dot 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 xn yn given at times t1, t2 so on till tn, if this factorizes as fx of x1 x2 dot dot xn specified at times t1 t2 dot 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 tn and fy of y1 y2 dot 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 yn and t1 t2 dot 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 tn, then we say that these two random processes are statistically independent. Okay. So, I specify all the times, I know what values I need to take. When I say fx of x1 x2, then I say fx of the random variable capital X at time t1 is less than or equal to small x1, comma the random variable x capital X at time t2 is less than or equal to t2, so on and so forth, using this definition that we have here, right. And if the probability distribution function, if it factors in this form, then these two processes are statistically independent. Of course, then you can prove some other results from this. If they are independent, are they uncorrelated, so on and so forth, right. You can sort of extend some of these results. So, we will pause here, we will take a break.